we continue with another interesting topic that is going to be generating poems with an RNN. This topic is going to be presented by Denis Krivitski. He is the Chief Technical Officer at Avoncourt Partners. Let's hear it from him.
Thanks for coming to my talk. My name is Denis. I come from Avoncourt Partners. We are a consultancy. We develop neural networks for our customers, mainly for natural language processing. I personally come from Israel. I've been here for half a year in Munich. I'm Russian born. I grew up in Israel, studied there in Technion. So that's in short about me. We're going to talk now about a neural network that can generate poems. It doesn't have any practical applications. Nobody actually needs poems generated by neural network. So why I think it's worth the time of sitting and listening to this talk? For three reasons. First, while I will actually describe how this works on the technical level so that you can understand and have a good idea of how things work there. By listening to this talk, probably you will have ideas of how to use this basis, extend it and somehow and make it useful in your domain. The second reason is if you want to make your hands dirty with implementing a neural network by yourself, just repeating this exercise is a very good place to start. So you could just listen to this lecture and then come home and implement it by yourself. And the third reason is because it's just fun. So let's start with redefining or rephrasing this problem. Instead of saying we want to write poems, let's say that we want to predict what a particular poet would say about a particular topic. What Shakespeare would say about love, what Pushkin would say about also love, and so on. Those are a couple of examples of what my neural network produced. Those were, to be honest, those were selected manually from a larger list of outputs. Not all outputs are interesting, of course. Yeah.
What was the last sentence?
The last sentence here, it's in Russian, it's Pushkin, okay? It's untranslatable, totally. Okay. Varona is a bird, so it would sound like don't bird with a bird. Okay, it also has a connotation of don't miss important things. Well, it just came out, it's just funny. So, first of all, let's break down this prediction problem. Instead of us trying to predict what a poet would say about a topic, let's break it down to a smaller problem of predicting what next letter a poet would write. Okay? So, for example, given the beginning of a sentence, okay, the problem is to guess what's going to be here. Can you guess it? Well, that's easy for us for two reasons. This specific question is easy for two reasons. Because, first reason, this sentence already appears in the training text, because Shakespeare have it in his text. Second, we want to predict the last letter in the sentence, and predicting last letter is easy because we have quite a lot of information before. Okay? Let's see a more difficult example. Okay, so it's E. Now, can you predict what's going to be here? It's a bit more difficult because we have some context, we have something, it's just meaningless, yeah, the sentence. The sentence ends here, we have a space, and then a new sentence begins. A new sentence could begin with many with many alternatives, all of them equally good. Okay, so it's pretty hard to say what Shakespeare would write next. Okay, so now we want a neural network that can take many characters as we want as an input, okay, to read all this, and produce one character as an output. One viable option for this architecture is recurrent neural networks. Recurrent neural networks are neural networks that eat the input recursively, okay, one character at a time, and then they remember something about the character that they read. So they could actually read the string, remember something about the string, and then produce a result. So we will use a recurrent neural network for this program. This is how it looks. The recurrent neural network has an input. Some A is the part that makes the calculation. It's a huge matrix of weights inside. We have a feedback loop. Okay, this feedback loop is the thing that remembers something from iteration to iteration, and we have an output. Now it helps to draw this new network in unrolled fashion. So we just draw it many times instead of thinking about the loop. Here our input goes in, and there our output goes out. So in our example, the input looks like this. Okay. So we look at the text as a sequence at our poems. Okay, it's a sequence of letters or a sequence of characters, including spaces, commas, and new lines. And we want the machine to predict everything, including where the spaces are between words and where the lines end, and so on. So what output we expect to get here? What would we expect the machine to get out? Do you know what is expected? Yeah, it's this. The same as input, just shifted by one letter left. Above T, we should get O. Above O, we should get space. Above space, B, and so on. This is what we should get. Now, what we actually get, of course, we do not get actually exactly this what we expect. Otherwise, we would have an ideal machine that predicts ideally. Well, that's not the case. This is an example of an actual output from my network. You could see that some letters were predicted correctly, and some letters were predicted not correctly. All the red circles are errors. So we have errors in our predictions. Now, what we want to do, we want to train our network as much as possible to produce less errors. In technical jargon, we call those errors loss. So we want to reduce the loss during the training process. This is an example of the graph of loss against time or against how we progress with the learning process. This is a real example from this machine. So it's when we started, it created a lot of errors, and very fast the number of errors reduced. And after some time, we get a plateau here when the machine could not learn anymore. So it reached its maximum ability or maximum precision. Now let's see some more examples. This is the input. Beforehand we had to be or not to be. Now it's the meaning of life. Why I changed the input? Because I want to test the network on inputs that do not appear in the training text. I want the network to be able to handle unknown text. Okay, so that's why. And let's see how the output of the network improved with the learning progress. So at the beginning, when we just start, this was the output. You can see here the training steps. The training process goes step by step, and the more steps we make, the smarter the network becomes. So here we have all the red letters are actually errors. Here we have a correct prediction, and in total we have 11 errors. Okay, after 11,000 iterations, we get a bit less errors than before. 30,000 iterations, a bit less errors. Okay, and gradually the amount of errors goes down. Now, you can see an interesting pattern here. First of all, the beginning of the sentence has more errors than the end of sentence. Okay, like we can see a red triangle here, and that's because the end letters are easier to predict, because when the machine gets to this last or one before last, it has a lot of context to look at, a lot of information to base its predictions on. The first letter is the hardest to predict because anything can go, so it's just a random choice. Another interesting thing here, here the machine predicted the letter correctly but missed the case. It should be small e. Okay. Let's go on. Now let's come back. So we started when I said we break down the whole prediction of poems into a smaller problem of predicting only one character. So I'm coming back to the larger problem. Now, we have a network that predicts one character. How can we write the entire poem with this? Or, in other words, how can we predict more than one character? We predict many characters. So we use the following trick. This is the same network in an unrolled fashion. Here comes our input. Okay? We already saw how we predict the next character after our input. Is just the application of the network. And then we take the output and put it again as an input. Or, in other words, we assume that this output is perfectly correct, and we relate to it as so it was a given thing, and then produce another output. In this way, we can generate as many characters as we want. We generate as long a poem as we want. Now, what is this? I told you at the beginning that we want the machine to generate poems on a particular subject. This is the subject, or in other words, we could say we start a poem with something, and let the machine continue. Okay, continue writing. We can look at the same network from a slightly different perspective, from a perspective that is used in machine translation. So we can say that this part of the network is an encoder that takes in the subject of the poem and encodes it into some mathematical representation in a vector that represents this subject. The second part of the network is the decoder. It takes this vector and generates the entire poem based on it. In machine translation, it would be as follows. The encoder would take in a sentence in the source language and generate some vector that represents the meaning of the sentence. The decoder would take the vector and generate a sentence in the target language. This is how the machine translation works. So we could say we translate the subject of the poem, it's the continuation of the poem. So now I want to show you the examples of poems. As before, I start with the first training step where the machine, here it's training step 1, it's 0 minutes into the training process, we just began. This is the poem that the machine generates. The theme is the meaning of life. It's just a random collection of characters, no more, nothing more, because the machine is untrained, totally untrained. Okay, after 140 steps or 5 minutes into the process, this is what we see. Now, what we have here, the machine realized the most frequent characters in the text. The most frequent characters in the text are spaces, actually. So it generates a lot of spaces. And then R and then E, just because R and E are frequent letters in English. That's it. Remember, we have a machine that has no prior knowledge of language, of letters, of anything. It just learns the language as we go. Okay, step 340, 11 minutes into the training. Similar, just we have more letters. S appeared, H, I, T, more letters appear. What we see next is, okay, now it already looks like text. Okay, of course it's not still text. We can still not have seen any meaning here. But the machine realized several things. First, we see play character names before paragraphs. Okay, the machine realized that in the source text, the play character names are written in capital letters with a colon at the end. So the machine picked it up. Okay, there is a colon and it's capital. Second, look at the spaces between the words. They appear natural. Okay, the letters themselves are still random, but the spaces are more or less resemble text. We also have some short and very frequent words appearing. They, I, he, on, our, me, because they appeared enough times in the text, the machine could pick them up. Also, what we have here, the machine picked up the concept of vowels and consonants and generates words where the consonants and vowels appear in a more or less natural order. Okay? The words are still not from, it's not an English word still, but it sounds like an English word. Here's a long string. If you try to read it, it sounds like an English word, we just don't know. Okay, now we are at step 940, half an hour into the learning process. And here we see longer words appear. Would, here, higher, more words appear. Okay, training step 1060, about 1 hour into the training process. We start to see sequences of correct words. Okay, here we see the fourth of the hands, the word to be the words of the. So we have a whole sequence of words spelled correctly. Okay, 3.5 hours into the process, we start to see syntactic structure in sentences. See this? Say that they are gone. We have subject, we have the verb and the object. Not everywhere. It starts to appear. Okay, syntactic structure. Okay, remember, what stands behind is a big matrix of weights that knows nothing about the language. "90 hours into the process. This is the best that this machine could achieve. Longer than this, it's just the same. It stopped improving. Okay, this is what we have. Yes, it's not Shakespeare. Yes, but as a software scientist, I'm fascinated by this enough. Yeah, of course it's not. We could read it. Yeah, the character names. Some of them are real because they appeared in the text, and some of them are invented by the machine. I also tried it in German. I guess here many people could read it and see this was created. This machine was trained on Goethe's Faust. It's technically for people who understand it's LSTM with 3 layers of 1024 elements in each layer. This is the best it could do. This is Pushkin. Well, for me, it's the best. It was funny because my mother language. For those who understand, you can read it. For those who do not understand, just trust me, it's great. Okay, so we have seen a neural network that can create, whether it generates poems, or at least something that looks like a poem. We looked at its structure and we saw examples of the text. The source code behind this lecture is in GitHub. You can go and see this and take pictures. I especially put a QR code here with a link to GitHub so you can take pictures and have this link. For those of you who want to try it on by yourself, you can go there and do this exercise. This exercise is really good because it's easy enough. You can develop it by yourself from scratch. There's nothing complicated inside. And it's complicated enough to meet several of the training process hurdles. You will have to overcome hurdles that require you to understand the meaning of batching and sequence lengths and how many letters you should consider at each training process, at each training step. Because if you consider too much, it doesn't converge. If you consider too low, the training stops, it doesn't go on. Also, things like gradient clip are also important to consider here because I know not everybody understands what it is, but without it, the network, after several hours of running, starts to diverge and stops learning. It just crashes. Okay, so that's it. We are Avoncourt. Actual, we are developing neural networks for customers. We are open for new customers. If it's interesting for any of you, please come to me, and I will be here after the talk. And I will be glad to speak with you. Thanks. Also, my colleague here, Cheret. Cheret, can you stand up so that people can see you? Please come to him as well if you don't catch me. And that's it. We are in the question and answers. Yeah, please.
Which is the easiest way to improve the quality? Because as for the project, it's okay, but if you would like to generate something like a news speech.
Okay, there are many ways to improve it. First of all, I would consider enlarging the network and running it on longer time. It's 3 layers of 3 layers by 1,000 each layer. We could put more units in each layer, more layers.
What is the reasonable limit for the layers amount?
The computation time.
Yeah, okay. Let's imagine we have a lot of computation time, and after the bottom amount of layers, network it does perform the same.
Yes, when you add more layers, remember that the training process goes using backpropagation. So we at every step we make a gradient, we calculate the gradients of the steps, and based on those gradients we decide how to improve the weights. Now, the more layers we have, the harder it is to calculate the gradients. We have the diminishing gradients problem. So I don't know where the limit is exactly. I didn't try to run it with 10 layers or 20 layers, but somewhere there the gradients will be too small to do anything. So this is one thing. Another thing that I would suggest to improve is look at the attention-based networks. Currently, the state-of-the-art algorithms that work behind Google Translate are based on attention mechanism. They are not recursive anymore. There's more advanced mechanism. Look on this, okay? Yeah, that's what I would suggest. Okay. Also, I made it character-based because my network looks at individual characters. It's possible to look at entire words and say, instead of having 26 characters in our vocabulary, we could have 100,000 words and work with this. I don't know, I didn't compare. What would be better? Okay. Thanks. Please.
How did you initialize the poem generation?
Initially, the poem generation.
You had to put something in the encoder before the first sequence, the first new character has been predicted.
Of course, that's
Somehow you must start with some CPU
yes,
characters.
exactly. This is what I did. Remember that I said we generate a poem in some particular subject. So I put the subject first. This is the initializer. Okay, here should be. Or you're asking about the state?
No, about what's really.
Yes, this is the subject, the meaning of life. This string goes here. Also, if you are very precise, there's also an arrow that should go here as in every other step. This arrow is random at the beginning, just random. Yes, please.
What computing time do you need to calculate the
On my laptop, it was 19 hours.
19 hours?
Yes, please. Words.
There is a problem with the poems, because poems is not writing normal writing. Poems means abstraction.
Right.
And there is no abstraction in such a network. It's abstraction in the features, the space, but not in the concept itself.
Do you ask about structure or abstraction?
Abstraction.
Abstraction.
So the fact of the poem, when you use a metaphor, what you are doing, you're putting content in a word that is different from exactly the word. So you are not representing exactly the word, but you are putting some content.
Yes.
So how to improve this? Do you have to do something that actually learn the abstraction of the concepts? I will go that way. So you need something like right now they use context, so you can put a network that learns more or less the context of the poem, and then one that actually has the grammar. That's all. So it's like speaking the poem in different.
So that's your suggestion how to improve?
No, that's what I see.
What do you see? Okay.
Could be.
Okay, thank you. Thanks for your suggestion. Any other question? Yes.
Not a question, just a comment. So last year I was talking about election stuff, if you remember the presentation from last year. Last year we built an annotator. So meaning we passed a lot of articles in the annotator to figure out the combination of words in a specific context. Meaning something like Obama, when do we recognize Obama to be the former president of the US? It needs some kind of context. And context can be analyzed. So personally, I like the idea of creating poems to AI, but it definitely would go to the words, not to the characters. And because that's interesting, if you look at your reading habits, words are more or less in context of another word. So there are combinations which are possible and others are not. So if we work with the probability of words being connected, it's much easier from my perspective to create something which might make sense. We have some examples from the entertainment industry, from movies. Yeah, we saw some examples in the past where movie companies try to use machine learning to continue writing a storyboard for film. And they use characters which were present in the story already, and said just teach the machine how to handle the characters. What is an animal? What does an animal be capable of? So what kind of classes are connected to that kind of thing? So I think at some point I could imagine putting all the pieces together, like we know how people react to emotions, we know how emotion will be expressed, we know how colors of a situation can be described, but we can teach a machine to write something which has sense, which makes sense.
Thank you. Thank you all. You have more questions. Do we have time or we should stop? Yes, okay, please.
Some question, the iterations, do you run it against vocabulary, or what exactly did you do in the iterations? And how could you define that one character was right and the other was an error?
Okay, that's a great question. So we are talking about this slide. Yes. I want to when my input is H, I want to predict the next letter. The next letter is E. It's here in the text. I know it. The machine still didn't see the letter, but I know it. So I expect at output, I expect to have the same input but shifted one character. In this way I know what I expect. Okay, I think it should be here. Yes, this slide. Okay, this is my input. This is my expectation. Now, when my expectation, when my actual output does not match expectation, it's an error. Yet it's a simplified view. Actually, it's a categorical cross and entropy. The machine outputs probability for each character, and the closer the probability to 1 for the right character and the lower for the others, the better it is.
How can the machine know probability? Does it have vocabulary?
Probability. The probability, okay, when my input is T, my output should be O. The probability for O is 100%. For other letters, it's 0. This is the ideal. Yes, I know the ideal because I have the Shakespeare text.
But who knows the idea? You or the machine?
Me as a trainer. Machine doesn't know. The machine gets something and then I correct it each time.
So you correct it?
Yes. Well, it happens automatically. It's not a manual process of 39,000 steps. Okay. Thanks for the question. Please.
Just trying to think of the suggestion of using words instead of letters. Words, 10,000 words in English is not maybe it's intractable computationally. Using embeddings of words instead of actual words as inputs, would that help, for example, to make it
Exactly. When I mean words, I mean using embedding vectors, of course, because it's intractable. Both there are two main approaches in analyzing language: character-based or word-based. Two of them compete. Something works better with the character-based, something works better with word-based. In word-based approach, we have a very large vocabulary and less elements in the string because we have words. In character-based, we have smaller vocabulary with larger number of elements. Yes, please.
For the previous question, generally, I think you can say character-based is less able to understand semantic. Like it would be very hard to, for example, generate very large articles or so, because it is very good for example, syntax or so, but it's very bad for semantic.
Yes, it's correct. It's correct. Also, remember that to train the network, we need large amount of examples. In this case, every letter in the source text is an example that we can use for training. The Shakespeare text is 4 megabytes, so it's 4 million letters. Now, if I go to words, I have less words, and I have larger vocabulary, so I need the entire Wikipedia, the entire Internet Archive, and so on.
That's it.
Thanks a lot for your questions. Thanks for being. Thank you, Denis.
Guys, we would like to thank all the sponsors and participants and the speakers for attending MI Summit, the one and only free event in Munich regarding artificial intelligence. It will become even bigger for the next years because we believe that the science should be hip and free. Yeah!